Started. Let's get started. So yes, today we are going to prove this main theorem which was stated last time, and that main theorem gives a bijection between the set of primitive extensions of degree p to the n of a p field k with the set of simple submodules, and these are simple gn submodules of those modules kn star bar or kn plus bar, right?
Sir, ln is
Okay,
close
so I'd call them ln. You are right. Ln star bar or ln plus bar. That's so this is what we are going to prove today. Before that, we need two little facts which are purely algebraic. This number 4 and there's this number 5. Oh, what happened to number 5? Yeah, here it is. Which I mean, number 5 is not purely algebraic. It's an arithmetic fact which we had done a couple of times ago. So let me just start with this one. So for this, you have to recall what this Schur-Zassenhaus theorem is, right? So the most general kind of statement of this theorem is that if I have a short exact sequence, 1, what should I call it? Gn G Q 1. So this is a short exact sequence of finite groups. And there's just one hypothesis. The hypothesis is that the order of n and q, the orders are relatively prime. There is no prime number which divides the orders of both these groups, the subgroup n and the quotient q. This is the hypothesis, and the conclusion then is so there are two conclusions, in fact. So the first one is that any such sequence admits a section. And the second conclusion is that any two sections, so you understand what a section is, right? A section is a homomorphism of groups from Q to G, such that when you apply that homomorphism S and then this projection pi, you get the identity map of Q. That's what a section is. And the second conclusion under this hypothesis that the orders are relatively prime is that any two sections are conjugate by an element of n. So that is the theorem of Schur-Zassenhaus. We have not proved it. I think to prove it in this generality is not an easy thing. We will need it on some very special cases, in some of those cases we have proved it. But today we are going to need a statement which is at the same time not so general and slightly more general. So let me explain what I mean. So here in this statement, this hypothesis is not going to be satisfied. So I need something where I need some information about splitting of sequences where the orders of the subgroup and the quotient group are not necessarily prime to each other. But the subgroup and the quotient group are going to be of somewhat special type. Here, they were completely arbitrary. right? N and Q are completely arbitrary finite groups. So let me explain what this new, what is the result that we are after. So here you fix a prime number L, and G is a finite group. And the hypothesis is that there's a normal subgroup A of G, which is, so we are given a prime L is fixed, right? The order of A should be prime to this L. So the normal subgroup A has order prime to L. And index, the index of A in G is a power of L. So what we have is an exact sequence A, G, A mod, or G mod A rather, G mod A, where this is some power of L, and this is prime to L. Wait a moment. So the hypothesis is satisfied, in fact.
Yes, sir, they have GCD wall.
Yeah. So the hypothesis, no. But wait a moment. Yeah. No. It's not satisfied. So see, in the usual Schur-Zassenhaus, so in the previous notation, when we had N, G, Q1, and these two were relatively prime orders, then the conclusion was, okay, let's just consider the case where this N is commutative. That's the only thing which I'll need. Here, right. Yeah. So, yeah. In the previous case where we had assumed that the orders of N and Q are relatively prime, let's further assume that N is commutative. Then the conclusion, there were two conclusions, right? And they can be neatly stated in terms of what's called co-homology, right? The first conclusion, the existence of a section, is neatly expressed by the vanishing of this H2. And the second conclusion, that any two sections are conjugate, is G, Q. That's the point. Yeah. So these two conclusions were, I mean, you get these two conclusions if N and Q have relatively prime orders, and moreover, N is commutative. Here, I'm looking at a slightly different thing. I'm not assuming this A to be commutative, and I'm not, and the conclusion I want is about H2 of G and C, and H1 of G and C. So what is C? So C is a simple FLG module of degree strictly greater than 1. So you see, I'll have some group G. I have a group G and I have a FLG module C, which is irreducible or simple, right? Irreducible is the same as simple. This is what is given to me. And my question is, when can I conclude that H1 and H2 GC are both trivial? That is the question. When is this going to happen? And this statement here gives you one condition under which this happens. So what is that condition? That condition is that, here it is. So the condition is that G, if G has a subgroup, which is normal, of order prime to L, this L is given to me, right? It's the same prime number L. So A has order prime to L, and the quotient is an L group. Its order is a power of L, the same L, right? So if G has such a subgroup, then I can conclude that H1GC and H2GC are both trivial. So that is the statement. This is the statement that we want to get. It's not exactly, I've told you what, I've explained what the difference with Schur's lemma is. Here, I'm getting the conclusion that H1GC and H2GC are trivial, even when all L may, this prime L, may divide both the order of G and the order of C. Where in the usual Schur-Zassenhaus lemma, your order of the, so you get the conclusion, when you get the conclusion H1 of Q, it was called N. Your conclusion was that H1 Qn and H2 Qn are trivial, but the hypothesis was that the order of Q and N are relatively prime. That was the hypothesis. And then you got this conclusion. Here, I want the same conclusion, but my hypothesis is, it doesn't say that the orders are relatively prime. In fact, there's a prime number which may divide both these orders, but there's a different hypothesis that the group G should have a normal subgroup A of order prime to L. So there's something about being prime to L here, and the quotient should be an L group. Okay, so that is a statement, and the proof requires a little bit of what is called group homology, right? So there's this thing called the inflation restriction. Sorry. Yeah, there's this inflation restriction sequence. Now, I don't know whether I've really explained H1 and H2 to you, but let me do it here briefly. So if I have a group G and M is a G module, so that means that M is what? It's a commutative group with an action of G. Then in this situation, you can define various other groups called H0 GM, H1 GM, H2 GM, H3 GM, and so on. So what are these things? G is any group, M is a G module, which is the same as saying that it's a commutative group with an action of G. Action of G means there's a homomorphism from G to the group of automorphisms of this commutative group M. So H0 is just the set of fixed points. I mean, this is a subgroup of M, and it consists of those elements of, so MG is just the set of all, let's say X in M, such that sigma of X is equal to X for all sigma in G. That's what is called H1GN. Right? This H1 is slightly.
Sir,
yes.
sir, here, sir, can you below the slide?
Sorry, say it again, please.
सर आपने जो ये एक्सप्लेन किया था कि जो G से ऑटोमॉर्फिज्म ऑफ M होगा या GL मतलब GL भी होगा, क्योंकि ऑटोमॉर्फिज्म जो इनवर्टिबल हो भी सकती है, नहीं हो सकती हैं.
Yeah. Okay. So there are two. You see.
I'm saying that you have defined that.
Okay. So I think I get your question. So you see, what happens is when E is a vector space over, let's say, FP, then of dimension, let's say, n. Then the group of automorphisms of E as a group is the same as GL n of FP. Same meaning, isomorphic. So that's the relation between automorphisms of a group and the GLN of NGLN.
Okay, sir.
So, for example, if you take all the automorphisms of the group Z to the 5, that's also going to be GL5 of Z. But I mean, one has to be somewhat careful. If you take all automorphisms, yeah. So, I mean, of course, this aught M makes sense even when M is not a vector space. So, in general, the definition is that it is just what? This is just a set of all.
Okay, sir.
It's the set of all mappings from M to M.
M to M.
Which are isomorphisms of groups. Huh? That's all. That's the group of automorphisms.
Okay, sir. So you are telling in more general setting.
Right. Okay, so let's remove this. Okay, so this is what H0 is. And this H1 is, I mean, sometimes it's called 1 cocycles modulo 1 co-boundaries. So, well, so basically, once you have G and M, right? You have this G and this M, then you can form this M sits inside. You can form what is called the semi-direct product, right? This is semi-direct product. So you have to recall what that is. So basically these 1 cocycles, you can think of them as sections here. So sections of the semi-direct product. And this 1 co-boundaries, they are really the same as conjugation. So what it means is if you have 2 sections, you can conjugate, I mean, if you have 1 section, and an element of M, you can conjugate by that element and get another section. So that's an equivalence relation, or I mean, the sections which are conjugate to the trivial section are all, they form a subgroup, and it's the quotient which is the H1. And finally, this H2 is, I mean, it classifies all extensions of G by M. So, I mean, these are all short exact sequences, 1 to M to E. So E is some group to G to 1, such that the resulting conjugation action of G on M is the given action. You are given an action here, see? So such extensions are elements of this H2, and two such extensions define the same element of H2 if they are isomorphic. So that's a little bit of group cohomology that you need to know. What is H0, what is H1, what is H2. Now, of course, I've already given you one extension of G by M, which is a semi-direct product. And this semi-direct product is actually the neutral element or the trivial element of the group H2. So if the group H2 vanishes, then every extension is basically this isomorphic to the semi-direct product. And therefore, it has a section. Conversely, you can show that if an extension has a section, then it is isomorphic to the semi-direct product. So the vanishing of H2 is the same as, basically the same as having a section. This is the vanishing of H2. And the vanishing of H1 is the same as saying that in the semi-direct product, any two sections are conjugate. Basically, that is what the vanishing of H1 says. So let's come back to the proof of this statement. So as I said, these cohomology groups, H1 and H2, they don't come by themselves. They are somehow related to each other. There are many sort of functorial kind of properties. So what happens is, initially you just have you have this group G and this G module C. But then you can take the invariance of C under this subgroup A, and that can be viewed as a G mod A module. So this can be viewed as a module over this group. And therefore, I can talk about H1 here. And then there's a natural map called inflation from this H1 to this H1. So basically, this H1, as I said, there are some sort of maps, right? One cocycles. So if I'm given a map from G mod A to CA, of course, there's a map from CA to C, that's the inclusion. And there's a map from G to G mod A, and therefore I get a map from G to C. That's basically what this inflation map does. Given a one cocycle here, it gives you a one cocycle here. And then there's the restriction map. The restriction map, so that's much simpler to explain. What is it? Yeah. So, of course, if you're given a map from G to C, and A is a subgroup of G, right? So you get a map from A to C. So this gives you the restriction map from H1GC to H1AC. And the point is that this sequence, which I've just now defined, is exact. This is an exact sequence. So once it is exact, I have the usual Schur-Sassenhaus theorem, which will tell me that this thing is trivial. That's because the orders are relatively prime. The order of A is prime to L, and the order of C is a power of L, right? C is an FP space after all, with an action of G, but it's an FP space has power, has order P to the FP or FL, FL. So the order is L to the, it's some L power order. So I first get this from the usual Schur-Zassenhaus. And then somehow, one gets the vanishing of this, and therefore you get the vanishing of this. Now, this inflation restriction sequence continues, and in fact, once you have this thing, H1GC vanishes, then you get an exact sequence involving the H2s. The same kind of inflation restriction sequence. And the same Schur-Zassenhaus here will tell you that this is trivial. And I mean, the same kind of argument will tell you that this group is also trivial. So this is what we wanted to prove. And what happened? So this requires a little bit of group homology, and well, okay. Right. And the final thing I want to recall before we come to the proof of the statement is the thing about irreducible FP representations of the absolute Galois group of K. Now, K is now a P field. Look, K is now not an arbitrary field. It's this local field, P field K. Right? And you are right. I mean, some of you remembered what Ln was. So you have a K here, then there was this Kn, and then there was this Ln, and that was a Galois extension with group Gn. And one of the theorems in a previous lecture was that every irreducible FP representation of this absolute Galois group of degree n factors through this quotient Gn. So why is Gn a quotient? Of course, you have K tilde, which is here. So this is the absolute Galois group. Everything is happening. So you have a natural map from the Galois group of the absolute Galois group of K to Gn, right? Because this comes from the inclusion of Ln in K tilde, right? And the point is that every irreducible FP representation of this group, I mean, representation of degree n, factors through this quotient Gn. So that's the other thing that I want to recall. And I'll now stop for maybe 2 minutes and see if there are any questions. Okay, if not, let's continue. So,
sir,
yes.
Can you explain what is the meaning of factor through?
Factors through is the following, that right. So it means that when I have a representation K tilde over K to, let's say, GLN of, what is it, FP, right? It's an irreducible and it's of degree n. Then I always have the kernel or yeah, I have the kernel. And then I have the fixed field of the kernel, right? To say that rho factors through Gn, rho factors through Gn is the same as saying that this fixed field of the kernel is contained in this Ln, right? Another way of saying it is, let's look at it this way. So let's look at, that's somewhat simpler, in fact. So as I said, I have this map from the absolute Galois group to Gn, right? Why do I have this map? This comes from the inclusion.
So inclusion.
Ln is contained
in K bar.
K tilde, right? So because of this map here, so I get another map, which is from the set of irreducible representations of Gn to irreducible representations of the absolute Galois group. So what is this map? If I call this one, I'll just call it iota. Then if I have a representation rho of Gn, I can first apply iota and then apply rho. So that's going to be a representation of this, right? So this iota will take me from the absolute Galois group to Gn. That's my iota. And then I have this rho, which takes me to Gn. Yeah. So this n, of course, yeah. So, and I have a irreducible representation of Gn of, so I should really be more precise. I should say FP representations of degree n. These are not arbitrary degree n. So irreducible, I'll get FP representations of degree n here as well. And so if I'm given a rho, which is an irreducible representation, FP representation of degree n of the group Gn, then I just compose with this iota and I'll get an irreducible FP representation of degree n of this absolute Galois group, right? Yes. And to say that, when I say that every representation factors through this quotient, what I mean is that this map here is actually a bijection. That is what is meant by saying that every irreducible representation of the absolute Galois group factors through this quotient Gn. It means that this natural map, which I've just explained, it's just the composition with iota, that is a bijection. Right?
Yes, sir.
So let me give you a simple example. So let's look at the group S3, right? S3, and you have this map to Z star. Z star is a group consisting of just +1 and -1. And this is the map which is sometimes called signature, right? I'll just call it S.
Yes, sir. Sign map.
Right. And I can say the following, that every homomorphism from S3 to C star factors through Z star. What does that mean? I mean, first let's understand what it means. And once you have understood this, you'll see that it's obviously true. So what it means is that, suppose I'm given a homomorphism Z star to C star. From this set, I have a mapping to the set of homomorphisms from S3 to C star, right? What is this mapping? If I'm given a homomorphism, let's call it chi, then I first apply this S here, the sign map, and then I apply chi. Then I'll get a homomorphism from S3 to C star, right? Because this S is a map from S3. Yeah, so it's a map from S3 to Z star. And then I have this map chi, which is taking me to C star. So the composite chi, this is a map from S3 to C star. Now, to say that every homomorphism factors through this quotient Z star means that this map is a bijection. Every homomorphism, the map from the homomorphisms of Z star into C star into the set of homomorphisms from S3 to C star, this map is
the bijection.
And that's clearly a bijection, right? Because
yes, sir. Yes, sir. Chi is related to chi dot S. Chi of S.
So it's in this sense that I meant that every representation factors through this quotient.
Okay, thank you, sir.
Every representation of this. So we are now talking not about homomorphisms into C star, but we are talking about FP representations of degree n of this group. And to say that they all factor through this quotient means that what is it? The map is going to be the other way. So these representations of Gn, so there's a map to these representations of the absolute Galois group. And this is a bijection. That's what it means. Factors through this quotient, right?
Yes, sir. Yes, sir.
Okay, so let's come to the proof of this parameterization. And what are the parameterization? If you recall, we had the set of primitive. Now K is a P field, right? That's given to us, and N is an integer which is given to us. We were looking at primitive extensions of K of degree P to the N. That was one thing. And then the other, this is the unknown set. And the other thing was simple submodules of degree n of the FP GN modules, GN module. And here it was either ln star or ln star plus, star bar.
Yes, sir. Yes, sir. Yes, sir.
Or ln plus bar, right?
Yes,
that
sir.
was the parameterization. Now I have to show that this is the bijection. Okay, So here is the strategy first. Let's first give the outline of the strategy. So first of all, I have to give you a map. What is this map? This map here, what is it? So E goes to what?
So ln P and root D.
Right. So you first start with a primitive extension E of degree P to the N over K. Then you have this E over K, right? And then you have Ln here. So you can form E ln. So the first thing to prove is that the extension E ln of ln, this extension is abelian of exponent P and degree P to the N. That's the first thing to prove. Then we will prove that this is actually not only, this is also Galois over K. And the resulting Galois module structure on this is simple. Meaning, then this group C will become a module over this group Gn, right? And C is an FP space because it's abelian of exponent P. So it's an FP space. So, and a Gn module because E ln is Galois over F. So this becomes a module over this. And therefore, this C becomes a FPGN module. And as such, it is a simple module. Okay. So once you have established these three things, then what will happen? First of all, this ln, if we are in characteristic 0, then it contains a primitive pth root of unity. And therefore, this extension ELN of ln, this extension will correspond to some simple submodule of ln star bar. ln, yeah, which is this. So it'll correspond to some D, which is a simple submodule here. And if it happens to be of characteristic P, then this D is going to be in Ln plus bar. That's Artin-Schreier theory here. It's Kummer here. Kummer, Artin-Schreier. Right? Such that ELN is equal to this in characteristic 0 and equal to this in characteristic P. Now, and so that will follow when we have established A. Now, when we establish B, then we will know that this D is Gn stable. Gn stable because this is Galois over K. And finally, so it's a Gn submodule. And finally, when we have established this, that C is a simple submodule, we will conclude that D is simple. So that will give you a map into the set of simple submodules of degree n. Well, not only simple, but this is going to be of degree n as well, because this D is of, because this is of degree P to the n, right? Here. Okay. So that will just give you the map in this direction. Once we have established these three things, we'll get this map. And finally, what are we going to do? Then we are going to show that this map is a bijection. So for that, we have to show that if we start with so now this E is being sent to D. So in order to show that it's a bijection, we have to see that every D comes from a unique E. That's the second thing that we have to show. That's this. So which says that every simple module D here of this or of this of degree n, there's a primitive extension here, so which is unique up to k isomorphism such that this or this. So that is what we have to do. Okay. So this number 16, it gives you the strategy of the proof, right? And this of proof of what? The statement here in number 4. This is the statement you have to prove. And now I've told you what the strategy of the proof is. So let's start and actually prove it. So you start with the primitive extension of degree p to the n. And now this is kind of more or less, we have been doing these things several times. So because it's another thing which we are using here is that it's automatically solvable, because this K is a P field and every finite extension is finite separable extension is solvable. So when you take the Galois closure, is it called L? No. This E hat is, so we have determined the structure of primitive soluble subgroups of Sn and so on. And we saw that there's a unique minimal normal subgroup, and that's of order p to the n, and so on. And the quotient is, so the quotient gives this extension L, that depends upon E. So there's a finite Galois, and the quotient, and that sequence splits. Okay, so this L is so there's a finite extension of K, which I'm calling L, such that this EL is equal to L is here, and when I take the compositum with E, I get E is here, right? And this is the compositum. I get the Galois closure of E. And moreover, this is a faithful and simple Galois L over K module. But we have also seen that everything factors. So because every irreducible representation of degree n, FL representation, FP representation, now we are looking at L equal to P, right? So it factors through Ln. So this L is going to be contained in Ln. And therefore, this E, which is, it's a totally ramified, it's a wildly ramified extension of K, and Ln is merely tamely ramified. So they're going to be linearly disjoint. Okay. So basically that characterization of primitive solvable subgroups of Sp to the n, that's one thing which has been used. And the other thing is this parameterization. Okay, maybe I have recalled it here. So where is this parameterization for arbitrary? Yeah, this here. So primitive soluble extensions of degree p to the n, it's called L to the n here, primitive soluble extensions. They correspond to pairs consisting of degree n FL representation rho, which is with soluble image, and something else. So this is what is needed. And the second thing that is needed is so that degree n irreducible representations of the absolute Galois group k tilde over k factor through this Gn. So that's what is needed. Now this is the converse. So you start with a simple submodule D of this or this, and so of degree D means it's of dimension, degree n means it's of dimension n over fp, and you just but it's not an arbitrary simple. Well, it's an arbitrary simple submodule. Submodule is important, so it's automatically Gn stable, right? And you put m equal to this or this, depending upon what the characteristic is, and C, let C be the Galois group. Then this m is going to be Galois over k, because this
Sir, after this, we have also proved that it is unique up to k isomorphism. Am I right?
Right. So first we are proving the existence, and then we have to prove the uniqueness. So we are first proving the existence, and the existence is basically it's going to come from. So you start with D here. That gives you this extension M, which is Galois over K, and then you will get what? You will get so the argument is here. Yes. So basically, so it's slightly, I mean, you just read this, but what happens is basically we are going to look at the maximal unramified P extension of K in Ln. So this is, okay. So here it is. You got this M, which is an extension of Ln, which is an extension of K. Here the group is Gn, and now what we have to find is an extension E of K such that E Ln is equal to this M. What we are given this M, and we have to find this E. Okay, right? Now
Yes, sir.
So the argument is something like this. So you take the maximal unramified P extension of K in Ln. Ln is here, so you have this P, and this is a P extension. Its degree is some power of P. So what are we going to get? We are going to get a sequence like this, right? One, let me go, I don't know what it is called. Has it been given some name? Yeah, it has not been given some name. Let me call it Hn. That's in Gn. And then the quotient is P, right? But this Hn, what property does it have? The thing is that this is going to be, I mean, because this is totally ramified, but it's tamely ramified. So its degree, the degree of Ln over this P is going to be prime to P. In other words, the order of Hn is prime to P. And the quotient is a P group. Now, that's exactly the kind of situation that we had considered here in this lemma. So this lemma was designed exactly for this sort of a purpose. So what is the conclusion going to be here? And I have this, so I apply it to this, I'm applying the lemma to Gn. What is called G there is my, what is called G there is this Gn, and what is called C there, right? It's called C. It's called C, yes. What is called C there is called C here as well. I've called it, yeah, C. So the point is that because this group Gn has such a subgroup whose quotient is a P group, I'll conclude that H1 Gn C is trivial and H2 Gn C is also trivial. Now, the vanishing of this H2 implies the existence of E. How is that? Because the vanishing says that there is a section, which means that there is a subgroup, and I can take the invariants under that subgroup, and those invariants give me an extension, and that's the extension E that we are looking for. But as you said, one has to also prove the uniqueness of this extension, and that comes from the vanishing of this H1 here. The vanishing of this H1 says that any two sections are conjugate, and which translate as saying that any two E's are actually conjugate over K. So that, I think, if you look at it, it's conceptually quite straightforward. It's not very convoluted, but of course there are some tools which you have to use. So let me just briefly sketch it again as to what I'm saying. So So basically, the existence of E has been reduced to the vanishing of H2GNC. And the uniqueness
H1GNC
of E, exactly, this has been reduced to H1GNC. Okay, now, well, if you don't, if you haven't followed this lemma very carefully, where is this purely algebraic lemma? I think it was after this. If you haven't followed it very carefully, let's look at the simplest case, which is when n is equal to 1. In that case, our G1, what is the order of G1? The order of G1 is P minus 1 squared. And what is the order of C? The order of C is P, because it's a we were looking at cyclic extensions of degree P. The situation there was that we had this P field K, and you had L1, which was just K to which you had joined the P minus 1th roots of everything in K star. Then we said degree P extensions, separable extensions of K, they were in bijection with FP lines in L1 star bar or L1 plus bar. G1 stable, we should call them G1 stable FP lines. And how did we get an extension E? What is the map? So you had these degree P extensions to these FP lines, G1 stable, right? And what's the map? E was being taken to the D if and only if EL1 was
L1 P under D.
Yeah.
P through.
Or if the characteristic was P, then it was
EL1 equal to L1 P inverse D.
Right. L1 and this P inverse D.
D.
So that gave you the map. But how did you show that this map is a bijection? You showed that, I mean, so you have to start with a D here, and you have to produce a unique E. Now okay, what can you do with this D? With this D, you can produce M, which is L1 to you adjoin pth roots of D, or you adjoin P inverse D. So now you've got M, you've got L1 here, and you've got K here. What you want is an E. E somewhere here, such that this is the M, such that M is equal to E L1. That's what you want. Okay. Now, in order to get this M, get this E, sorry, to get this E, you just look at this exact sequence, right? I mean, this M was supposed to be Galois over K. So you get this exact sequence 1 to the Galois group of M over L1 to the Galois group of M over K to the Galois group of L1 over K. That's an exact sequence. And here, what are the orders of these groups? This group is of order P, and this group is of order P minus 1 squared. So the usual Schur-Sassenhaus will give you what? That H1 is trivial and H2 is trivial. This H2 is trivial gives you, I mean, so it gives you a section. And if you look at the image of this inside this, that will give you a subgroup of this. So once you have a subgroup of a Galois group, you can take the fixed field, and that is going to be the E here. This Galois group of M over K, this is here, and you take the fixed field and you'll get some extension. But how do you know that you have not, that extension doesn't depend upon the section that you have chosen? It doesn't, because any two sections are conjugate and
by H1. By
the vanishing of H1. And therefore, any of these two extensions are going to be conjugate over K. Right? So that's the broad outline of the proof. That was the case n equal to 1. And the case of arbitrary n is conceptually very, very similar. The only difference is that in order to get the vanishing of H1 and H2, you have to use this somewhat more general lemma. It's not very direct, this vanishing of H1 and H2. Doesn't follow immediately from Schur-Sassenhaus, but it follows from Schur-Sassenhaus after you apply what is called this, if you take into account this inflation restriction sequences. And that's what we had, what we have used. Okay, so that completes the proof. I've written it down completely, right? So you can take a look at it. And there's one thing which, maybe a final thing which I want to add, which is the following. Okay, so let's. Yeah, so this is, I don't know how to introduce this, but okay, so what remains after this? So that certain number of things. Oh, goodness. Can you hear me?
Yes, sir. So, but your PPT is not visible.
Just a moment.
Okay, sir.
Is there now? Good. Yeah,
Yes,
so
sir.
what are the things which remain? Now, so our this primitive extensions, just a moment, huh? Right. So primitive extensions of k of degree p to the n, these we have parameterized in terms of simple FPGN modules in is a better word, submodules, right? In ln star bar or ln plus bar of degree n. So we have established this bijection. But as we did in the case n equal to 1, we have to now make this one more explicit. So that is where we need to know the Galois module structure of this ln star bar or ln plus bar. What is it as a Galois module? I mean, and that is what we had done in one of the lectures, using this lemma due to Iwasawa, which was slightly technical, but which involved just natural numbers. And that lemma is very useful, right? Another remark, so that will actually determine all simple submodules of these two modules. So our parameterization is something which will actually help in finding these primitive extensions. For example, I mean, there are these examples which have been treated here, right? Quartic and octic examples. Quartic examples are when p is equal to 2 and n is equal to 2. So you are looking at extensions of degree p to the n, which is 2 to the 2, which is, so these are called quartic, right? And octic, that's when p is 2 and n is 3. So you're looking at p to the n. So p to the n is 8, and these are octic extensions. Are there no nonic examples? Because you can also look at, you can also look at, so I think one should try p equal to 3 and n equal to 2, right? So you'll get p to the n, which is 9 here, and you should be able to write down all nonic extensions of course, a triadic field. Because we are looking at a p-adic field, right? And okay, so the final remark is, I don't know which way to say it. So one way of saying it is that if you have a P field K, and if you have a totally ramified, or I mean, doesn't have to be totally ramified. If you have a finite, let's just take a finite separable extension, then you have the different, right? The different of E over K. And that is some PE to the power CE over K, right? The different is an ideal of the ring of integers of E, and therefore it is a power of this maximal ideal. So you would like to compute this coefficient CE over K, because that's what determines the different completely. And this here does precisely the computation. So it says that if you have any wildly primitive extension, it just means that the degree is a power of P, right? And then this is the differential excess. So this can be called the differential coefficient or differential exponent. This here is called the differential exponent. But if the degree is, let's say, m, then I can look at, look at CE over K minus m minus 1. This can be called the differential excess. Because I don't know whether you remember this, if you have E over K totally ramified, and it's tamely ramified of degree m, then the differential exponent, the CE over K, is actually equal to m minus 1. Or rather, I could say it this way. Suppose you forget, you don't put tame in the hypothesis. Let us take totally ramified of degree m, then the differential exponent is equal to m minus, it's always greater than m minus 1 with equality if and only if this E over K is tame. So this tame ramification, if it's tamely ramified of degree m, then the differential exponent is m minus 1. And therefore, whatever the difference is, that's called the differential excess. So this is always positive and strictly positive if and only if it's wildly ramified. Okay, so that this here computes this differential exponent. This epsilon E is the differential excess, and then there's the unique ramification break of C, etc. I mean, there are, I don't want to go into the entire notation, but I think I must have done it in the case n equal to 1 when I talked about Serre's, the proof of Serre's mass formula. So in that case, so this is a direct generalization from the case n equal to 1 to an arbitrary n. Okay, so that's one, that's the other remark. And those of you who are interested in doing something interesting by themselves, they are invited to consider. So I've given these examples of quartic and octic examples. So you are invited to look at some nonic examples, which is, you look at, for example, you just take the field Q3, and you write down all primitive extensions of Q3 of degree 9. What are they? Not only how many are there, but what are they? You should be able to write them down. And actually, if you want to do such a thing, I would advise you to do something much simpler first, which is, so instead of looking at degree 9, you should look at degree 3 first, right? And you should try first to try all degree P extensions of QP. So that's the case, n equal to 1. Here, we are looking at n equal to 2, but we are restricting P to be 3, right? And in these examples, I'm in fact restricting P to be 2 and n to be just, yeah, so that's because you have to compute all these irreducible representations and Galois groups, and you have to do a lot of things. But yes, I think those of you who have followed this course and who want to understand what has been done should try to parameterize the set of all degree P extensions of QP. And then not only should you be able to write them all down, I mean, of course, you should be able to answer how many, but that's a simple, I mean, that's a much weaker question than what are they? I mean, what are all the degree P extensions of QP? In particular, how many there are? And you could ask there for what their differences are. What are the difference of these extensions? You can ask not only the different, but what are the other thing that I wanted to say? Yeah, for example, you could ask which ones are cyclic? Which become cyclic over a quadratic extension? You can ask various kinds of questions. So, and this, whatever we have done, answers all these questions. All these questions can be answered by whatever we have done in the case n equal to 1. That's the simplest case that you can think of. And actually, we are, what we have done is for arbitrary n, right? So one should be able to write down all primitive extensions of degree p to the n of any p field k. Okay, so the next thing that you can try to do after you have done this for degree p extensions of QP is to look at, you keep n equal to 1, n is still equal to 1, so you're now looking at degree p extensions, not of QP this time, but of FP power series T. This also you should be able to write down. Now there are infinitely many. So, but you can still ask, what are the difference? Or the differential exponents? What are the difference of all these various extensions? Which ones are cyclic? And all these things. You can ask all the analogous questions, right? And I think you should all be in a position to work this out. It requires a little bit of work, right? But at the beginning of the course, we had no idea how to write down any extensions of these P fields apart from maybe quadratic extensions. Even quadratic extensions of Q2, we weren't, they don't follow the usual pattern of quadratic extensions of QP when P is odd. Because when P is odd, you have only 3 quadratic extensions. But when P is equal to 2, Q2 has 7 quadratic extensions. And similarly, I mean, so that is the simplest case. The 7 quadratic extensions of Q2, that is the simplest example of n equal to 1, and that's the case n equal to 1, P equal to, well, that's the case n equal to 1, P equal to 2, and in fact, K equal to Q2. So that would look at, you're looking at quadratic extensions of Q2. Have we also looked at all quadratic extensions of F2 power series T? If not, you should do it first, because that's the case n equal to 1, P equal to 2, and in fact, K equal to F2 power series T. So these are very special cases of what we have done. And in general, you should be able to do these things now. So since this is the last lecture, here is one last opportunity for all of you to ask any questions you may have. Or, I mean, of course, I'm there on email, and you can also send emails to me if you have any questions regarding this course. Unfortunately, I'll not be able to answer other kinds of questions which you may have about mathematics or about life, but questions about this course, I'll be happy to try to answer them.
सर इसमें कोई रिसर्च एरिया है आगे रिसर्च करने के लिए, मतलब इसमें हम रिसर्च कर सकते हैं आगे किसी टॉपिक पर?
That's right. So you see these, the answer is yes. I mean, there are various questions which arise from this, and so here is one question which you can straight away ask. So we were looking at this P field K, and we were looking at only primitive extensions. So let's also take the special case n equal to 2, right? I mean, n equal to 1, this question doesn't make sense. So n equal to 2 is the smallest case where it makes sense. So suppose I have a separable extension E of K of degree P squared, right? N is equal to 2. It's an extension of degree P squared. So there are 3 possibilities. The first possibility is that it could be primitive, meaning there are no intermediate extensions. The second possibility is that there's a unique intermediate extension. And the third possibility is that, in fact, there are P plus 1 intermediate extensions. So first you have to convince yourself that there are only these three possibilities. There's a primitive, either primitive, which means there are no intermediate extensions, or there's a unique intermediate extension, or there are p+1 intermediate extensions. You can't have p-1 intermediate extensions or p intermediate extensions or something. Right?
Yes, sir.
Okay. So that's the first thing that you have to convince yourself of, you have to try to prove. Now, the next question is, okay, these primitive extensions, I know how to handle these. And
Yes, sir.
you should also be able to handle these ones. Because this is the case where actually the extension is probably going to be Z mod PZ2 extensions. I mean, it's a compositum of two cyclic extensions. So that's an abelian case. So the question arises, what happens in this case? Can you write down? So the primitive extensions and this Z mod PZ cross Z mod PZ extensions, they are easy to write down. So the question arises as to what are the extensions which have a unique intermediate extension? Can you sort of parameterize them explicitly? So that's a very simple question which arises very naturally in this context. And once you start exploring this kind of questions, more questions will arise. You will understand something, just as if you go travel a little bit, then you see further away, right? You can see more things and you can ask. Similarly, once you have started working on such small, I mean, I don't know whether it's going to be very small, but it's a problem which arises naturally at this stage. Once you have started working on such a problem, you will come across many other questions. And you'll be interested in those questions because you have yourself come up with them. They're not somebody else's questions, they are going to be your questions. And yeah, so I'm sure there are lots of questions which arise in this area, because this is a sort of vast area. And what is the general theme? The general theme is, what are all the finite separable extensions of a given P field? Yeah, so here is another question which arises. So suppose I have a P field K and I have a degree P extension, and then I have K2, which is also a degree P separable extension, right? Or I have two of them, K2 and K2 prime. So so K2 and K2 prime are not K1 isomorphic, but they may be K isomorphic. When are K2 and K2 prime K isomorphic? Similarly, so instead of degree P, you can look at primitive extension of degree P to the N. Degree P to the N, primitive extension. So here, maybe you just start with, okay, primitive degree P to the M, etc. So there are various questions which arise, and the general theme is going to be, given a P field K, write down all finite separable extensions of K. Now, if you are interested in abelian extensions, that's class field theory does it. If you are only interested in tamely ramified extensions, in one of the lectures we have done it. If you're only interested in primitive extensions, then we have done it. But these are all special cases. The general cases, all finite separable extensions of K. I don't know whether anybody can do it explicitly as we have done it for primitive extensions. So that's exactly, I mean, my time is over, and that's the ultimate question in this sort of theme.
Thank you, sir.
Right?
For
Okay.
this.
Before the session ends, I would like to say something. On behalf of all participants, I would like to thank Professor Dalawat for giving us a course on local arithmetics for last 5 months. We learned many new topics from this course, and we enjoyed it too. Wish you a very good health ahead, sir.
Okay, thank you very much. Thank you. So you people can write an email to me if you have any questions or any comments about the course, questions about the content, anything is welcome. But well, about related to this theme of local arithmetic. Right, okay. So thank you for attending this course, and best of luck to everybody. Right, I'm going to.
Thank you, sir.
Right, I'm going to end this session. Right.
Thank you.
Thank you, sir.
Bye-bye.
Bye, sir.